I'll be solving problem A6 on the 2004 equivalent competition. So it looks like a very interesting integral problem, but integral inequalities can be sort of tough. What's easier to prove with inequalities is summations. So if we replace both sides with a Riemann sum, it might be easier to show. The question is, how do we know that this solves the problem? Well, suppose that we had a function. You can also see it as the left-hand side is the limit as n goes to infinity of the Riemann sum here, and the right-hand side is the limit as n goes to infinity of this Riemann sum. And if an is less than or equal to bn for all n, and the limits an approaches a and bn approaches b, then a is less than or equal to b. But we want convenient points for the Riemann sum, so we might as well divide up the square 0, 1 squared into n squared points. And we substitute those points in. This is the inequality that we get. We can start rearranging this by multiplying by n to the power of 4, and then move everything over on one side. After we do that, we see that all the terms are of the form aij times akl for some ijkl, which makes this left-hand side a quadratic form. Now, how do we show a quadratic form is greater or equal to 0, which is to say it's positive semi-definite? We can show that the matrix associated with the quadratic form only has non-negative eigenvalues. First, we need to construct the matrix. So we'll have to look at the coefficients and then divide the coefficients that are not along the diagonal by 2. So if we take a look at aij squared, that appears n squared times here. It appears once here, and then it appears once here and once here. That gives us n squared plus 1 minus 2n, which is equal to n minus 1 squared. Now if we take a look at aij times aik, where j is not equal to k, it appears twice here, one product in either order, aij times aik or aik times aij, and then it appears exactly once here, but then again the product is in either order. We would have it as aij times aik or aik times aij. And similarly for aji times aki. Now, if these all four don't line up, I is not equal to k and j is not equal to l, well, then it doesn't appear here, it doesn't appear here, but of course it appears twice here, because this includes all possible n squared, and then the square of that sum of n squared terms. Now, this is the convenient order that I chose for the quadratic form, so that when I wrote it down, it would be very symmetric, as we'll see later. We'll define B to be the n squared by n squared matrix associated with the quadratic form, and then the rows and columns will be in this following order. It'll be 0 indexed rows, 0 indexed columns, because with zeros everywhere, we can use the modulus function, we can use the floor function, and it all works out very nicely. And we'll see this definition implies, well, not definition, but this consequence implies this. If I equals j, then we have this form where it's aij times aij. Well, keep in mind the ij here and the ij here are different. This is ij from 0 to n minus 1. This is ij from 0 to n squared minus 1. But if these pairs of indices are equal, we see the coefficient here is n minus 1 squared. Now, if the floor of I over n is equal to the floor of j over n, that's the case where these first two are equal, ai, j, and ai, k. If ai is congruent to j mod n, that's the case where these two are equal, the last two. And that gives us 2 minus 2n, but we divide by 2 because it appears on either side of the diagonal. And the other case is, of course, just 2 when we divide by 2 and we get 1. If this is hard to follow, I recommend taking a small value of n and then just writing everything out. Now, you probably shouldn't do this because I already have the matrix written down for m equals 2 and n equals 3. We start to notice some patterns. If we divide this up into 4 smaller matrices, these two are the same, these two are the same, and these are actually opposites of each other. And maybe the pattern will be even harder to see here, but because of just how many ones there are, if we start defining the all ones matrix, we'll see, well, this is just the all ones matrix minus 3 times the identity, and it's the same here, 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 here. So then we can just define j prime as that, all ones matrix minus n times the identity, and we'll have j prime here, 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 and then here we'll have minus 2 times j prime. That allows us to rewrite it in this form. And again, using this definition, we can prove that this pattern generally continues. But still, we need to find the eigenvalues of B, so how is this going to help us? Well, you can see the self-similarity here after we collapse an n squared matrix, an n squared by n squared matrix into an n by n block matrix. The j prime also has the diagonal property, and we could just define the all j primes matrix and then subtract stuff off the diagonal to get j double prime. How do we capture this self-similarity? Well, it's j prime times j prime, where this is now the Kronecker product. We can define the Kronecker product A times B as starting with the matrix A, then for every entry in the matrix, replace it with that entry times the whole matrix B. You'll have just a bunch of copies of B, one for each entry of A, scaled by that entry of A. And again, this is a bunch of computation to show a little bit of symbol manipulation to show that this is actually the case. But once we have this, the rest of the problem is quite easy, because if U, V are eigenvectors of A, B, if eigenvalues lambda 1, lambda 2, then U cross V is an eigenvector of A cross B with eigenvalue lambda 1 times lambda 2. The eigenvalues of J are n and 0, so the eigenvalues of J prime are 0 and minus n. So then the eigenvalues of B could be 0 times 0, 0 times minus n, and minus n times 0, or minus n times minus n. So either 0 or n squared. And these are non-negative forces, so we're done. And as an aside, how do we know that these are the eigenvalues of J? Well, J has rank 1, so the null space has dimension n minus 1. So the eigenvalue 0 appears n minus 1 times. And since the trace of the matrix is n, and the sum of the eigenvalues is the trace, the missing eigenvalue is n. Now suppose that we did not know about the Kronecker product. Or maybe we knew about it, but we were not convinced while doing the competition that maybe the graders would accept this sort of reasoning. Well, we can pretend that we didn't arrive at the solution of the Kronecker product and just not write that down, but even knowing about it could give us some motivation as to what the solution may be. Suppose we suspect the eigenvalues are just 0 and n squared. Maybe we just took this case, n equals 2, and we found it was 0 and 4. And it's like, well, that's good enough for me. Then the minimal polynomial will only have factors x and x minus n squared. If b is diagonalizable, then the minimal polynomial will be exactly x times x minus n squared. So we'll have b squared is equal to n squared b by Cayley-Hamilton theorem. And if we just show b squared is equal to n squared b, then we can work backwards. We can get the minimal polynomial divides this, and every eigenvalue is either 0 or n squared. And this is a lot simpler calculation. There's a lot fewer things to prove. We could just go back to the block matrix definition, which will just be exactly one step from the actual values of b instead of all the multiple steps to justify the Kronecker product and everything, and then just calculate brute force. First we write down b in block form, and then we just take these are the entries of c, and we go through this whole summation process. But before we do that, we're going to get j prime squared, so we need to know what j squared is. J squared is equal to nj. You can do that computation on your own very easily, and then just expand out j prime squared. Finally, after we have that, we arrive here. And if we sum this, if I is not equal to j, alright, forgot to mention, this is the Kronecker delta. Delta ij is equal to 1 if I equals j and 0 otherwise. If we sum this across all k, this term will only be 1 when k is equal to I. This term will only be 1 when k is equal to j. Their product will only be equal to 1 when I equals j equals k, and otherwise it'll be 0. So there'll be exactly contribution of n squared when I equals j, otherwise it's going to vanish. And this is just going to give us n. This is going to give us contribution of n exactly when k equals I. This is going to give us n when k equals j. And then we get finally n squared Cij, which then shows that c squared is equal to n squared c. And then these are block matrices, so we get b squared is equal to n squared b. Now, as to maybe how would you conjecture this even if you had no intuition about product and self-similarity? Well, you could do what I did and plug in this 9x9 matrix into a calculator, and it tells you what the eigenvalues and eigenvectors are. You might not be able to do that on an actual competition, but it really helps with the motivation for the problem.